Hello, this is the presentation of the technical paper, A Hybrid Approach Combining Control Theory and Artificial Intelligence for Engineering Self-Adaptive Systems. This work was published in the International Symposium on Software Engineering for Adaptive and Self-Managing Systems, SIMS 20. My name is Ricardo Caldas, and the co-authors are Arthur, Eric, Genaína, Thomas, and Patrizio. During the presentation, I will go through the problem that we solve with our approach, backed up on an exemplar system. Then I will detail our solution and the many parts that compose it. Finally, I will present some results of the evaluation session and our main findings. It is important to assure that the system that is being engineered behaves accordingly to its purposes, especially during and after adaptation. And this problem was highly studied in control theory communities. However, when it comes to systems that engineers cannot have precise assumptions on its operating conditions, applying such techniques can be hard. Take as an example the pacemaker. Once engineers precisely model the relation between the necessary electrical current and heartbeat rate, they can implement a PID controller that will stay for years in a patient's body. Even if we add features to this pacemaker, such as Wi-Fi connection, the relation between current and heartbeat rate does not change. On the other hand, imagine that a team of engineers have the task of designing a network of sensors to collect human vital signs. And then, suppose that this network will be deployed in an intensive care unit. Such systems are prone to large set of uncertainties. For example, which sensors will be used? Or how many of each sensor type will be used? Will all the sensors be from the same manufacturer? The patients might have different characteristics and needs. How will the system adjust to that? Well, environments like these demand robust, reliable, and flexible systems that are able to cope with distinct settings and desires. Modeling a system as the BSN might be hard at design time. To address this concern, the engineers usually rely on modeling the system in a higher level of abstraction. This means that the controller configuration must be done during the system execution, when precise assumptions can be derived from the system behavior. There comes our first question. How could AI aid the optimization of controller parameters so they can be more meaningful to the domain of operating system? Also, searching for these configurations can get time-consuming due to its often large solution space nature. So we raise our second question. How to apply AI-based techniques in the search of adaptation solutions in control theoretical self-adaptation strategies? To tackle those questions, we propose an intertwining between control theory and AI in a two-phase optimization approach, where hierarchical system manager tighten up the gap between high-level requirements and internal knob behavior. Here, we refer to hierarchical in the sense that we are promoting a separation of concerns between the components that form the system manager. And each of these components are aided by non-dominated sorting genetic algorithms 2, or NSGA2, for the ones familiar with it. Such algorithm aims at assisting the synthesis of adaptation strategies and enforcing them alongside control theoretical properties. We build our solution on top of an architecture composed by the knowledge repository, system manager, and managed system. We call it hybrid because we make use of control theory and artificial intelligence to continuously achieve the desired goals for the managed system. Control theory to enforce guarantees, and artificial intelligence to lead to an optimal solution with less effort. In the next few slides, we will dig deep into each of the architectural components. First, orthogonal to the other components, the knowledge repository contains three artifacts: a parametric formula, the managed system goals, and system information. The parametric formula is a model that represents the system's behavior in high level. During runtime, such formula can be completed with information regarding the system execution and can be used for calculating quality of service properties. The goals are the objectives to be achieved by the system with respect to functional or non-functional requirements. And the system information is a set of events and data about the status of the target system collected during runtime. We propose a separation of concerns between a model-based high-level reasoning element, the strategy manager, and a control theoretical enforcement element, the strategy enactor. Here, the strategy manager is responsible for selecting a strategy that will guide the system into reaching their goals based on their system requirements. The strategy enactor will enforce that this strategy is followed by the system. At last, optimization procedures were tailored for the two levels of components in the system manager. The manager optimization assists the synthesis of strategies. The enactor optimization collects information of previous adaptations and improves the strategy's enactor into enforcing the current strategy. In the following slides, we detail the strategy manager and strategy enactor of our hybrid approach, with emphasis to their optimization. Responsible for high-level reasoning, the strategy manager synthesizes adaptation strategies based on a parametric formula, goals, and the current status of the observed property. Imagine, for example, that the modeled global reliability of the BSN by a composition of the weighted reliabilities of the sensors. The goal is to achieve a reliability RD, and the observed properties are the reliabilities of the sensors. The system manager configurations are the offset that indicates at which point the search begins, and the granularity that indicates the slope of the increments. The algorithm iterates sequentially on each term of the formula until the dependent variable reaches the goal, or the independent variable reaches its limit. In such case, the algorithm loops through the other independent variables until the goal is reached or not, indicating that a strategy was found or not. The optimization aims for identifying suitable values for the granularity and offset parameters, which makes the strategy synthesis more efficient in the domain problem. Here, we could say that the optimization problem being resolved is what values of granularity and offset minimize the time to solution, where the search space is the set of positive real numbers that offset and granularity can assume depending on the property that is being analyzed. The procedure here consists of the depicted optimization pipeline. The first step is to collect data from an execution of the system, such as the relation of time to solution, granularity, and offset for each instant. Then, we use a curve fitting method to learn the model. Third, we use the learned model as an input for the NSGA2. Here, the evolutionary algorithm encodes a candidate solution as a chromosome. The fitness function is the minimization of the time to solution as well as the limits of the parameters. In this sense, the optimization is constrained by the domain problem. The outcome of the third phase is an optimal or near optimal configuration. Finally, the configuration is applied to the system. Detailing now the strategy enactment level. The strategy enactor is responsible for enforcing an adaptation strategy on the target system. Here, the feedback control loop is the underlying structure that guides the strategy enforcement. The strategy is defined by a goal, a condition, and a set of actions. The goal is used as the reference of the feedback loop. The condition and actions are encoded into the controller, which can be divided in two blocks, One checks whether there is the need of adaptation using the condition, the other performs an action in the system. Finally, it is necessary to have a component monitoring and analyzing the system status that will be compared to the goal, and the loop begins again. For instance, in our case study example, we implemented a PI controller that adjusts the sensor sampling rate based on the error. The error is given by the difference between goal and the status. The condition evaluates if the error is bigger than 3% with relation to the goal. And the action consists of a setting of sensor sampling rate according to the PI equation, parameterized by Kp and Ki, the proportional and integral gains. Given the abstract level of our model in design time, the Kp and Ki may lead to a suboptimal controller depending on runtime conditions. Therefore, we employ an AI-based optimization technique to tune the controller's parameters. Here, our optimization goal can be summarized by what values of proportional and integral gain minimize the overshoot, steady-state error, and settling time, where our solution space initially comprises the combination of real numbers that Kp and Ki may assume. For this procedure, we employ the same optimization pipeline as we did before in the manager optimization. Here, we exemplify the second step, learn model, where we apply the curve fitting technique for the relation between overshoot and integral gain. In the leftmost graph, the blue marks are stable executions of the system and the red are unstable. One can see that the Ki is directly proportional to the overshoot, and with bigger Ki values, the more likely to lead into instability. After applying the curve fitting method, we obtained a linear model which is depicted in the rightmost figure. With the models in hand, then SGA2 can be executed. At this point, the evolutionary algorithm produces a set of Pareto optimal solutions depicted by the circles in figure 8. From these ones, we can choose either the green one that optimizes the overshoot or the blue one that optimizes the steady-state error, or something in between, depending on the desired trade-off and requirements. Our proposal was evaluated through the execution of the BSN, implemented in robotic operating system. We applied the goal question metric method to assess the experimental setup and execution. Finally, we presented and discussed the results. This instance of the BSN consists of 3 sensors: the electrocardiograph, the thermometer, and the pulse oximeter, which, configured by certain frequency, collects the vital signs of the patient and preprocesses it and sends it to the central hub. Then, the central hub fuses and processes this data and evaluates whether the patient is in an emergential state. In this scenario, we implemented a system manager that collects reliability level of each component, and based on that, adjusts the sampling rate of the sensors. For experimentation purposes, we designed a scenario where the sensors floods the central hub and the sensors fail sporadically, with impact on the overall system reliability. Finally, we logged the actuation signals and the reliability status over time. For evaluation purposes, we defined 2 goals. The first is that there is a desire to improve the time to find an eligible adaptation. So we raised the question: how much time does the optimization pipeline takes to find a solution? Here we want to collect the duration in seconds of the pipeline execution. Second, there was the desire to improve the quality of the adaptation. So we raised our second question: how efficient is the proposed learning and optimization? Then we based our answer on the control theoretical properties, overshoot and steady-state error. To answer question 1, we first executed the BSN multiple times, while varying the strategy and actor configurations. Then, we instrumented the optimization pipeline for collecting how much time has it passed on phases 2 and 3. Finally, we executed both phases for the collected data. Our results are summarized in this table. Each value here is represented in seconds. As one can see, for the manager optimization pipeline, the learning model phase took more than the NSJ2 execution, totalizing in 0.31 seconds. As for the Enactor optimization, the learning model phase was faster in comparison with the NSJ2 execution, that took 5 seconds for KP and almost 5 seconds for KI, totalizing in 10 seconds. It is important to mention that our NSJ2 execution makes 10,000 function evaluations, but this amount can be reduced without much loss, if the pipeline effectiveness must be improved. For the second goal, we executed this scenario for 50 distinct strategy enactors configurations. Then, we applied the learning pipeline on top of the collected data, which resulted in a near optimal configuration for the KP and KI values. With the gains in hand, we executed the system one more time for the sake of comparison to the other configuration results. For instance, the near optimal configuration chosen by our approach was the proportional gain equals 114 and the integral gain equals 0.75. The graphical representation of the explored adaptation space makes the distinction between unstable solutions in red, stable solutions in purple, and the black dot, which is our solution. Here, the yellow dashed lines mark the upper bound requirements for overshoot and steady-state error. One can see that there are some possible solutions that could be even better than the black mark chosen by our algorithm. To better understand that, we plotted the box plot for each of the executions with respect to the metrics. In these graphs, the chosen execution is the configuration number 1. As you can see, it is lime green because 100% of the executions under this configuration have stabilized. Also, there is a small value of standard deviation and the average is within the requirement boundaries, which is compatible to other seemingly good solutions, such as 16 and 17. Wrapping up, our hybrid approach combines control theory and AI to optimize the adaptation process, in which we employed NSJ2 algorithm to efficiently synthesize adaptation strategies and strategy enforcement through control theory principles to guarantee continuous goal satisfaction. Finally, we conclude that our approach could lead the system into finding near-optimal solutions while also improving the adaptation loop, according to well-known control properties. Furthermore, we plan to work on integrating the optimization pipelines into runtime and further explore evolution algorithms in this experimental setup. Thanks for your attention. For more information and further discussions, don't hesitate on contacting us.